Hi, and welcome to this kind of 5-minute, maybe a bit longer than that, overview of CI312 at the University of Brighton. This is a final year, so level 6 undergraduate course called Computer Graphics Algorithms, delivered by myself. I am Aidan Delaney, and I'm just going to go through a little bit of what's presented on the course. So, what kind of topics do we discuss? I suppose you could break it down into three main themes. First, we're going to look at some data structures for representation of graphical assets in memory. So, when you're playing around with Blender and you're modeling with the meshes on screen, how do computer program actually represent those meshes internally for ease of manipulation? The other thing we're going to look at, or one other thing that we're going to look at, are the actual algorithms to modify those meshes. So how do we do stuff like smooth the meshes or something pretty like that? And the final thing we're going to do is actually study the study of algorithms themselves. So what does it mean for an algorithm to be fast? You know, when we're talking about running algorithms on meshes, we're talking about running algorithms on data that could be, you know, anything from a couple of hundred vertices to a couple of million vertices, all connected up together. So what's a fast algorithm? If an algorithm's fast on a mesh with 100 vertices, is it still fast on a mesh with 1,000,000 vertices? Or you know, basically, what are the trade-offs when writing an algorithm? Here's an idea of kind of what we might cover in each of the 12 lectures. This would skip, or we might kind of remove topics here and there, or put in other topics depending on how people are finding this stuff, or what people think to be more interesting. So obviously I begin with an introduction, and we're going to mainly concentrate on stuff like subdivision. So how do we subdivide surfaces? This is really cool stuff. I mean, it was comes from a lot of work by Ed Catmull, so Catmull and Clark. So these are the people who founded Pixar. This is the stuff that you probably first saw in the cinemas in Toy Story, but it's been hanging around for actually a long time, since the 70s. And the algorithms that we're going to be looking at on the course are actual algorithms that were used in Pixar's later movies. Cars is one example of one of the algorithms that we're going to look at. We'll have a look at mesh representation. We'll have a look at a specific algorithm called butterfly subdivision. We'll then have a look at Catmull-Clark subdivision. We'll have a look at some spline interpolation, and we might need some required math for the spline interpolation. Is really cool. Given a number of points drawn on screen, how do you interpolate a smooth curve through those? I use it quite a bit in my research for sketch recognition. So if we sketch something on the screen, what you've got are a bunch of XY time points, and how do you draw a nice smooth curve through that under certain kind of constraints. We might then look at NURB surfaces, non-uniform rational B-spline surfaces. They're really powerful technique for modeling, and a really powerful kind of concept that they're very nice. The kind of way we're going to look at NURBs will be kind of surface level. We'll understand the spline interpolation stuff, but the NURB stuff, I just really want to see. I really want you guys to see how, if we extend the maths into another dimension, the spline interpolation stuff will be in 2D. If we extend it into 3 dimensions, and if we talk about control surfaces rather than just control points, the kind of power that you can get from it, it's quite cool. So then I might then talk about the hardware graphics pipeline and shaders. Those of you who are on the computer science games course, you've got some of this from last year at CI312. There's no harm in topping it up. We might look at it in a bit more kind of detail at some respects. We'll start at a nice high level and break it down into the components. Then, you know, the study of algorithms themselves. We're going to have a look at algorithmic complexity. What does it mean for an algorithm to be complex? How fast are algorithms? And then we'll have a look at the notation for describing that. And then the crux of algorithms, you know, the big question in computer science. What is the big question in computer science? And the big question is, does P equal NP? We'll define the question and we'll explore the answer a little bit. We don't actually have an answer right now, and that the first person who does get an answer to this question will be a very famous computer scientist. Then we'll have a look at the limits of what can be performed by an algorithm. But as I said, this stuff can change depending on the kind of topics that you guys are interested in, and depending on how we're dealing with a lot of the contents of the course. What kind of resources do I have for you? Well, a lot of academic papers. You will get the original papers on butterfly subdivision and Catmull-Clark subdivision. They're really well written, surprisingly, for papers that are from way back in the 70s. Often it's older papers are more difficult to read because they use older terminology, but these ones are just actually really well written papers. Obviously the course notes will be on Student Central, and the laboratory sessions will be used to back up an awful lot of this. So what we'll be doing in the labs is actually putting a lot of this into practice, so not just looking at different mesh representations but trying to implement them in the labs. Finally, the assessment. It's the same kind of assessment that I've been running for several years now, so 40% coursework, a 60% open book exam, and the coursework is normally to just implement an algorithm, and you'll get the coursework on the first day of the course. So it'll be on, let me check, it'll be on Monday the 3rd of October. The assessment will appear online. There's my contact. I'm a.j.delaney@brighton.ac.uk, and I hope to see you guys in lectures quite soon. Thanks for listening. Bye.